Good morning, everyone. We'll start the last day of the school with David. Please go ahead.
Okay, thanks a lot. So, as review from last time, we ended up talking about representations of the conformal group again. And one point is that it's very useful to use index-free notation when describing spinning operators. So we had this traceless matrix tensor operator. It's very convenient to contract it with null polarization vectors to get a function of a position and a null vector, z. So z is null, and this position is just in Minkowski space. And writing things in this way makes it clear how to at least start to make sense mathematically of an operator with non-integer spin. The idea is that we can generalize this type of object by just imagining that it's no longer polynomial in the polarization vector. So we allow a general function of a position and a null direction. This function has to be homogeneous of degree j in the null direction, but other than that, it's unconstrained. And it has to transform like a primary. And so that's the mathematical way of describing a non-integer spin operator. And whereas in this case, when we had a polynomial in Z, it was possible to go back to some kind of underlying tensor. In general, with a general continuous spin operator, there's no underlying tensor. You're forced to use this index-free notation. Okay, so let's talk about some of the properties that these things would have if they existed. So one thing that we can immediately ask about are correlation functions of these guys. And if we consider, for example, a three-point function of two scalars and an operator with spin j, then that three-point function is famously fixed by conformal invariance. And so this is the only thing that you can write down consistent with conformal invariance. But we have to specify a little bit more information depending on what kind of correlator we're looking at. So in a Whiteman correlator, then let's say we're interested in a product of operators with some particular ordering in Lorentzian signature. Then this ordering instructs us to use a particular I epsilon prescription. So before we talked about how you need to take the times and give them tiny imaginary parts, where the imaginary parts are ordered in a way that depends on the ordering of the correlator you're interested in. So in this case, the imaginary parts would have to be ordered in this way because we're interested in a correlator where we have phi 2, then O of x3, and then phi 1. And so this gives you some I epsilon prescription that you should actually apply to this expression to really make sense of what it is. And so, for example, using these shifts, you can check for yourself that every time you see x13 squared, you should replace it with x13 squared plus I epsilon t13. Okay, so that's an exercise. So in general, this procedure of giving small imaginary parts to all the times tells you how to go around any branch points in this quantity when you move the points around. Okay, so now we're going to be interested in operators with non-integer spin. So what happens when we allow j to be not an integer? And let's first ask that question in Euclidean signature. And in Euclidean signature, you can immediately see that there's some kind of problem. There's no problem with the denominator, but there's a problem with the numerator. And the reason is that in Euclidean signature, in order to satisfy the null condition, it requires that z is complex. So it means that this numerator factor, which I'll call V312, it means that V312 is complex. And so we have to be careful about defining fractional powers of it. And in fact, not only is V312 complex, but you can verify for yourself, and I recommend doing this exercise, that by moving around the points, you can get V312 to move around the origin an arbitrary number of times. So it means that non-integer powers of this quantity are actually not single-valued in Euclidean signature. So there's just no way to make sense of a continuous spin operator in Euclidean signature, and that's consistent with the intuition that you probably came into the school with, that continuous spin operators don't make sense because we usually think about operators in Euclidean signature. In Euclidean signature, you can never have non-integer j. So you can get V312 to wrap around the origin an arbitrary number of times, and that implies that j has to be an integer in Euclidean signature. So in Lorentzian signature, the situation is different. So first of all, we can have real null vectors. Second of all, the fate of this quantity V312 depends on the I epsilon prescription for the correlator. So we can study different types of correlators with different I epsilon prescriptions, and we'll find different behaviors. So for example, if you study this guy, then you should try to convince yourself that using the I epsilon prescription appropriate for this ordering, you can indeed get V312 to wrap around 0 by moving around the points in the correlator. You can study this ordering. And in this case, turns out that V312 does not wrap around 0. And then finally, this one, it does wrap around 0. So what this means is that if we want to make sense of a three-point function containing a continuous spin operator, then only these three-point functions make sense. You conclude from this that any continuous spin operator, if you evaluate a Whiteman function like this, so now let's really take O to be continuous spin, then these Whiteman functions, where O acts on the vacuum, have to vanish. That's the only thing that's consistent with the analyticity structure of the correlator and conformal invariance. Okay, so we learned that continuous spin operators kill the vacuum, and only these types of Whiteman functions make sense with continuous spin operators. And another consequence of this is that if you tried to study a three-point function that had the analytic structure of a time-ordered correlator, and that involved a continuous spin operator, then it would never make sense. The reason is that in a time-ordered correlator, when the points are space-like separated from each other, you don't, the time-ordered correlator doesn't tell you how to pick the ordering of the operators. You're supposed to be able to pick any ordering you want because the operators are supposed to commute at space-like separation. That's what usually happens. But in this case, if you have an operator space-like separated from a continuous spin operator, then you're supposed to be able to choose an ordering where the continuous spin operator acts on the vacuum, and that's 0. And so it means the whole thing is inconsistent unless the whole correlator is 0. So Whiteman functions where the continuous spin operator acts on the vacuum vanish. Time-ordered correlators with continuous spin operators don't make sense. And the relationship between time-ordered correlator, so another way to understand this is that time-ordered correlators are Wick rotations of Euclidean correlators. So the fact that time-ordered correlators of continuous spin operators don't make sense is just a restating of the fact that Euclidean correlators of continuous spin operators don't make sense. They have the same problems. They have extra branch cuts that either ruin conformal symmetry or ruin your ability to define the correlator at all. Okay, so these are some pretty weird properties. So we probably at this point should be asking, well, do these things even exist at all? Like, why should we even think about these? And so, whoops, let's see here. So now I want to describe a very natural way in which these objects appear in any CFT. And I want to convince you that you should already think about continuous spin operators. It's already a very useful language for some interesting physical questions. We talked a little bit last time about the embedding formalism. The upshot with the embedding formalism is that you can lift operators to the embedding space, and this is a very useful thing to do. So here capital X and capital Z live in 2 higher dimensions, RD, 2. And you can define a lift of an operator in flat space to an operator in the embedding space. And this lift is designed so that it has a very simple conformal transformation properties. So the flat space quantities little x and little z are defined in terms of capital X and capital Z in this way. And there's an inverse map where you just take the embedding space correlator and you evaluate it at some special values of capital X and capital Z. And remember, our embedding space coordinates are x plus, x minus, x mu. And the advantage of defining this object is that if the flat space operator transforms like a primary, then this object transforms in a super simple way where the conformal transformations just act linearly on the coordinates. Okay, so I'll write that again. The advantage of this object is that O of capital X, capital Z, when you hit it with a conformal transformation, just becomes O of that conformal transformation acting as a matrix on the coordinates. So it's extremely simple to analyze the consequences of conformal symmetry for these objects. Some other comments about these. So this object O of capital X and capital Z is defined on a subspace in the in RD, 2, where all of these quantities vanish. So you remember x squared being equal to 0 was part of our condition for getting the projective null cone in the embedding space, which was our way of describing how Minkowski space sits inside the embedding space. These conditions have to do with reducing the number of degrees of freedom in this capital Z polarization vector to be equal to the number of degrees of freedom in the little z polarization vector. And then there are a couple other properties that this thing satisfies by construction. One is that it's homogeneous in these capitalized variables. So if I rescale x and rescale z, then by construction this goes like lambda to the minus delta, alpha to the j, O of x comma z. And then another property that you should check for yourself is that there's a gauge redundancy where we shift z by x. So whenever you have an object that is a function of embedding space coordinates satisfying these conditions, that's homogeneous and gauge invariant, then it describes a spin J operator, a spin J primary operator. Okay? Questions? Good. Okay. So now you'll see why it's really useful to use this language. I'm going to define a conformally invariant integral transform.
Sorry, David, so
Yes.
you just argued that these operators might make sense in CFTs, and what about generic QFT?
What about general QFT?
Yeah, so.
Yeah, I mean, I think the fact that these operators, as we'll talk about later, make sense in general CFT means they should make sense in at least a QFT that's a relevant deformation of a CFT. But actually, I think it's a really interesting question how the relevant deformation interplays with all the stuff we're going to talk about. And I'm not sure how well studied it is. Okay. So this integral transform is called the light transform. And it's sort of it's a Lorentzian cousin of the shadow transform that we talked about several days ago. Okay, so the light transform is easiest to write in the embedding space. So it takes an operator O of capital X, capital Z to an integral of O with this funny replacement. So why on earth would you do this integral? Well, we can check that. So first of all, everything here is manifestly covariant under SOD, 2. Okay, so that takes care of conformal invariance. This is a conformal invariant transformation. But we should also check some things. So for example, we should check that this squared equals 0, and this squared equals 0, and furthermore their dot product equals 0, because those are necessary requirements for evaluating this O thing on the right hand side. And you should check for yourself that all of these things are indeed true. And furthermore, you can check gauge invariance. So you can check that O of x comma z is equal to O of x comma z plus beta x. And this is just shifting alpha to alpha plus beta in the integral. Okay, so I encourage you to look at all the consistency conditions that this object is supposed to satisfy and check that this thing indeed satisfies all of those consistency conditions and therefore is a conformally invariant integral transform. And this integral transform does something really interesting. So we can just figure out the homogeneity of this thing in x and z. And I'll let you guys do that exercise. And you find that this is lambda to the minus 1 minus j, alpha to the 1 minus delta, L of O of x comma z. And this means that this transform changes the quantum numbers of the operator it's acting on from delta comma j to 1 minus j comma 1 minus delta. This is the analog of the case of the shadow transform. So the shadow transform took delta to d minus delta. And an important consistency condition for that, the existence of that whole thing, was that the conformal Casimir eigenvalue is preserved under that replacement. So that was something we checked. So you can check again that this replacement preserves C2 of delta J. It's not totally obvious, so you have to do a little bit of algebra to see it. But in fact, this turns out to be true. And these kinds of transformations that preserve the Casimir are called affine Weyl reflections. We've seen another place where an affine Weyl reflection showed up, which is in Karen-Ho's formula. In the Lorentzian inversion formula, there was a really funny conformal block with dimension and spin swapped, plus some shifts. You can go and check that that's an affine Weyl reflection. Okay. And in fact, the fact that that affine Weyl reflection shows up in his formula is a clue that we should be thinking about these kinds of integral transforms. Okay, so this is a transform that
David?
Yes.
So that means we can just think of this as some, over here.
Sorry.
Some group transformation, then? It just belongs.
That's right, yeah. There's a more abstract definition of what an affine vowel reflection is. It's a reflection in the root system that preserves half the sum of the positive roots.
Yeah, so do you know what generator specifically this is?
What vial generator of the vial group?
Yeah, like
I mean,
maybe the shadow transform is the Hamiltonian or some like combination of it, and this one is with a certain angle.
I don't know what you mean. I mean, these are vial reflections, so they're specified by how they act on the weights, and I'm telling you how they act on the weights. Yes?
Do you know the holographic dual of these operators?
Okay, well, let's be a little more specific about what the operator looks like, but then that's a great question. So let me return to it in just a second. Any other questions? I want to describe what the boundary picture of this operator looks like first, just a little bit. Okay. All right. So there's this interesting integral transform that one can do. And so let's take a look at what it's actually telling us to do. So we can write this in different. So I think it'll be useful to use this dictionary that you now can't see, but I can see it, so I can use it to write this transform that you also can't see in more conventional coordinates. So I'm just going to use the dictionary between the embedding space and flat space to rewrite this transform. So it's an integral, again, d alpha O of z minus alpha x, comma minus x. And we're going to take this and evaluate it at these special points to go from the embedding space to flat space. Before we do that, it's useful to do a little bit of reshuffling. So first of all, we have gauge invariance under shifting this thing by a multiple of this thing. So using that, so let's see, I didn't write down how the shift is. So we have this gauge invariance, and then we also have homogeneity in both of these arguments. So using those two facts, we can rewrite this as an integral with some weight of capital X minus capital Z over alpha, comma Z. Evaluated at these interesting points. Okay, so here you use gauge invariance to turn this into a Z times minus 1 over alpha, and then you pull out a minus alpha to these various powers from both factors, and you end up with this and this. And so now we can, having written it in this way, we can go straight to flat space by plugging in these special values, and you get an integral from minus infinity to infinity, d alpha minus alpha to the minus delta minus j, O of x minus z over alpha, comma z. So if someone handed you this, it would be very weird and surprising that it's a conformally invariant integral transform that implements an affine vowel reflection. But this formula, it's completely transparent. So that's the power of the embedding space. So let's look at what this actually is doing. So it's an integral transform. And so when alpha is equal to minus infinity, this operator is sitting at some point x. So here's x. And this is the point alpha equals minus infinity. And as we increase alpha from minus infinity, the point moves in the z direction. So it moves in the direction of z. And as alpha goes to 0, the position diverges to null infinity. But null infinity is not a special point in a CFT. We can choose a different conformal frame that has a different notion of null infinity. And this is just, again, the Lorentzian version of the familiar fact, probably familiar, that the point at infinity is not special in Euclidean CFT. Okay? So the null infinity is not special, and what we should do is just keep going. We should keep going, and when we do that, we're going to move into the next Poincare patch, or Minkowski patch. So remember that CFTs can be analytically continued to live on the Lorentzian cylinder, which is tiled by different Minkowski patches. And here, we started out in one patch, but we can just move to another patch. And so we move to the next patch, and the place where we end up is this point that I called Tx. It's this special point in the next patch that has the same Minkowski coordinates as the point we started with. Another way to say it is that it's the point you get by starting with this point and sending light rays in all directions and seeing where they converge. So you might remember that we did that exercise a while ago to find what Tx was. And so this is an integral transform that goes between these 2 points. And so now I can answer your question, which is that the light transform of a local operator, it's the integral along a null line on the boundary. And typically what it does is it creates some kind of shock in the bulk. So you have, here's ADS. You have along the boundary, you're integrating an operator from some point around the boundary of ADS like this, and this will create some kind of excitation in ADS that's localized on a null plane. So, for example, the classic example of this is when you take the light transform of the stress tensor, and this is the so-called average null energy operator. Here I'm just making the statement that when you insert the average null energy operator on the boundary, it creates a gravitational shock in the bulk. Okay, and actually maybe I wrote that a little too early because it's maybe not totally clear from what I've done. So let's look at this light transform in a different conformal frame to make it clearer what the connection is to the Anik operator. Choosing a different conformal frame just in the embedding space just amounts to choosing some different z's and x's. So now I'm going to make a different choice. I'm going to choose x naught is minus 0, 0, 1 half, 1 half, 0. So here these are coordinates on r d minus 1, 1. I singled out the first 2 coordinates. Then the rest of the coordinates are 0. And this is x plus and x minus, these embedding space coordinates here. And z naught equals 1 comma y squared comma 0, 0, y, where y is in rd minus 2. The only consistency condition on these choices is that they have to satisfy the condition that x naught squared and z naught squared are 0, and x naught dot z naught is 0. If I can find any 2 embedding space vectors satisfying those conditions, then I'm allowed to evaluate the operator at those vectors. Okay? So you can check that the dot product of these are 0 and these are both null in the embedding space. So let's plug them in and see what we get. What you get is that this light transform evaluated at these points is the integral from minus infinity to infinity d alpha, and then so we have O evaluated at some polarization vector, which here I've taken to be pointing that way. So that basically picks out all the V components of O. So these are spin indices and they're being set equal to V. And we're sitting at U equals 0, V equals alpha, and at some Y. So this is the integral of O along a null direction in Minkowski space. And you can see that when you choose this conformal frame, there's no funny weight in the integral. It's just an unweighted integral along the null direction. Yes?
Sorry, what do the indices in the O mean?
Yeah, so O has spin indices. So I'm not writing it in index-free notation just in this line. So mu1 through mu_j. And then I'm picking light cone coordinates. Yeah, I should have said that. So little x is equal to u comma v comma y with metric minus uv plus y squared. Okay, and so then this is, does that answer your question? So then this is like, you have a tensor, you can plug in 1 for all the indices or 2 for all the indices, and here we're plugging in v. Sometimes people use plus minus notation. So this would be O plus 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 plus. Okay. Good. So this is a pretty familiar object. It's a very natural thing to study. And the claim is that this thing transforms like a continuous spin primary. In particular, the Anek operator transforms like a primary operator with dimension -1 and spin 1 minus d, which is a pretty weird fact and maybe not obvious from this definition where you plug in t for O to study the Anek operator. But it's very useful to know that when you're studying correlators of the Anek operator in a CFT, because this fact lets you constrain the correlators. Okay. Okay, so this is one thing that you can do to get a continuous spin operator, and it's a very natural operation, but it's also going to be a key ingredient in everything that we do next. And in particular, we're going to need a really important fact about the light transform, which has to do with our more abstract discussion of continuous spin operators. So remember, we were looking at the analytic structure of correlation functions involving continuous spin operators, and we had these weird conclusions that certain Whiteman functions had to be 0. And so now we're going to see how those conclusions come about in the particular case where a continuous spin operator is the light transform of a primary operator. So the thing that we concluded by looking at the analytic structure of correlators was that Whiteman functions that involve a continuous spin operator acting on the vacuum were 0. Okay, so we were just looking at 3-point functions. That made the analysis easier. But actually, it turns out that this is true for any correlation function. It's just a statement that this state is 0. Okay, so a continuous spin operator claim. So claim a continuous spin operator annihilates the vacuum. And we're going to check this claim for the case where O is the light transform of something. Okay, so in particular, the light transform of a local operator annihilates the vacuum. So we need to check this in order to verify that these properties of 3-point functions that we were talking about before, purely from analyticity considerations, are realized for these particular continuous spin operators that we've constructed. Okay, so and not only that, but this argument will show up again later when we prove the inversion formula. Okay, so to do this, let's think about a Whiteman function, and it can have any number of insertions. They don't have to be primaries. And we're going to take L of O acting on the vacuum. And this is CFT, so we can pick any conformal frame we want. And let's pick the conformal frame where the light transform is the simplest, which is the one that we just analyzed over there, where it just becomes an integral along the v direction. So it's an integral of O at u equals 0 v y. Okay, so now we get to use some fun facts about analyticity properties of Lorentzian correlators that we talked about previously. So you might remember that we showed that there is a region of holomorphicity for Lorentzian correlators. And the region of holomorphicity was that the imaginary parts of the spatial positions are ordered in a particular way. So the imaginary parts of the positions in the correlator are ordered like this. And the last position in the correlator here, I'll just write it out explicitly, is 0 and comma, well, we're taking imaginary parts, so we get the imaginary part of v. And for simplicity, let me assume that y is real. So we just get this vector written in light cone coordinates. So again, we're using these light cone coordinates u comma v comma y in R d minus 1, 1. Okay, so this is the regime of analyticity of this Whiteman correlator, and it just follows from positivity of energy. And this is the QFT generalization of this statement that I made earlier about ordering of the imaginary parts of the times. Okay, so the correlator is analytic in this region. And in particular here, just to start with, the object that we're starting with, in order for it to even make sense at all, these x's, these imaginary parts of x's, have to be chosen to be very tiny, but in this ordering. Okay? So the Whiteman function to begin with is defined by approaching from this region where the x's are ordered in this way, and where the imaginary part of x is less than 0. So that means in the past, points in the past of the point 0. And so now you can see that it means that if we look in the v plane for this integral that we're doing, the correlator is holomorphic up here. It's holomorphic in the upper half plane. If you want to dig into this a little more, what's happening is that if you take v and you give it an imaginary part, then that's equivalent to inserting into this correlator e to the imaginary part of v times null energy. And the null energy is positive, so it's e to the minus that. So we're sticking in e to the minus a positive operator, and that's never going to ruin analyticity. Okay? So we're free to move in this direction. Everything is perfectly fine. And what that means is that as long as the boundary conditions on this integral are well behaved, we can take this integration contour and deform it into the upper half plane to get 0. And so you can argue that the boundary conditions on the integral are indeed well behaved. And it just has to do with the fact that the endpoints of the integral are at null infinity, and null infinity is not a special point in CFT. So you can just go there and look at how the integral is weighted at null infinity. And you find that it's sufficiently well behaved as long as delta plus j is bigger than 1. Okay, so just purely from the analyticity properties of correlators, we can conclude that the light transform of any operator kills the vacuum. Questions? Yes?
Sorry, I did not get why does this imply that the non-integer spin kills the vacuum?
So what I'm trying to check here is that the light transform of an operator kills the vacuum. Okay? So this claim about a general non-integer spin operator killing the vacuum, that follows from our analysis earlier with 3-point functions. It actually would follow from an analysis of 2-point functions. Because if you can show that the correlator of something with in any 2-point function is 0, then it's just then the state is 0. So, so we actually established this more general claim earlier. But now I'm just trying to check this special version of it more explicitly.
Yeah, my point is I did not understand the more special version. Why does your analyticity... What's the argument there that says the L of O analyzes the vacuum?
So the argument is that, so this is a correlator involving L of O. We're going to try to argue that any Whiteman correlator where L of O acts on the vacuum is 0. And if that's true, then this state has to be 0. Okay? So we're going to check this, and so let's study this correlator. This is the light transform of O inside the correlator. It's an integral over the v direction. And then you can just check that the integrand is holomorphic in the upper half v plane. So you can deform the integral to get 0. Okay, so let's see. Good. So the light transform of an operator kills the vacuum, and that's consistent with our analysis of 3-point structures earlier. And so now we can ask about the 3-point structure that doesn't necessarily vanish. So let's take O to be in the middle and take the light transform of it. And let's say we have some O of dimension delta and spin j. Then we basically know what this is. L is a conformally invariant integral transform that exchanges delta and j in a particular way. And transforms like a primary, and 3-point functions in primaries are fixed by conformal invariance. So this thing has to be proportional to the 3-point structure, the only possible 3-point structure where we just exchange 1 minus delta and j in this way. And here I'm using this funny notation where when I write a correlator in the state 0, I just mean the unique conformally invariant structure for operators in those representations. Okay, so I don't mean a physical correlation function. So that's what this notation means. This is just what happens where I take the function of positions that I wrote down at the beginning of this lecture, which is the unique conformally invariant 3-point function. I apply this integral transform to it. The claim is that I get back the unique conformally invariant 3-point function with these quantum numbers swapped, times some coefficient. And if you want a fun exercise, I encourage you to try to compute the coefficient. Okay, it's just an integral, but I think doing so will give you some insight into how all this stuff works. In particular, it's kind of fun to do this crazy integral of this thing and see the structure of a 3-point function of primaries pop out. Okay, and so one last thing that we'll need is to study the light transform of a time-ordered 3-point structure. So what that means is, let's take a 3-point structure and give everything the I epsilon prescriptions appropriate for a time-ordered correlator. Equivalently, you can think of this as a sum of Whiteman structures with theta functions enforcing certain time orderings. And we'll just take the light transform of this thing. So what is that? So we know that the light transform, so let's draw the points 1 and 2. We know that the light transform kills the vacuum. And so this means that if you can rewrite this thing as the light transform of a Whiteman function where O acts on the vacuum, then you have to get 0. So let me give you an example of when you can do that. Let's suppose that x is down here, and the light transform integral just goes from here to here. So x is always in the past of these two guys. So in this time-ordered correlator, I can think of O as always being on the right. And therefore, this time-ordered correlator is equal to a Whiteman correlator along the entire integration contour. And therefore, the light transform has to vanish in this case. Was that argument clear? Okay, here's another slightly trickier case. So let's suppose, let me draw the light cones of 1 and 2. Let's suppose that x is here, and the light transform contour goes like that. So then it's actually still true that the answer is 0, And you might go, oh, well, that's not so good because X starts in the past of these guys and ends in the future of these guys. But it starts space-like separated from these. So in the region where it's space-like separated, I can still reorder the operators in the time-ordered correlator, because operators at space-like separation commute, and think of O as acting on the vacuum, acting on the future vacuum. And then by the time it gets out here, it's just in the future of everything, so we can still think of it as acting on the future vacuum. Okay? So both of these cases vanish. And the only way to get something non-vanishing is if the light transform contour does this. It goes from the past of 1 to the future of 2. There's another way to write this condition, which is, so let's draw a Minkowski space here. Another way to write this is that X is in the past of 1, and so xt is in the future of 2, so that means X is in the future of t inverse 2. So here's t inverse 2. Sometimes I like to write this as 2 minus. So that's the point in the previous Minkowski patch with the same coordinates as 2. And the statement is that X has to be in this diamond. So we get some theta function that says that 1 is in the future of X, which is in the future of 2 minus. And in that situation, the time-ordered correlator is equal to the Whiteman correlator, where we have 2, O, and then 1. And so this thing multiplies the light transform of a Whiteman correlator, which is this, which we know. So you should also convince yourself that along this entire integration contour, the time-ordered correlator is equal to a Whiteman correlator with O in the middle. Yes?
About being 0. Would you distinguish being 0 in the original inverse space or taking you to a different superselection sector?
V0? What is
the light operator acting on the vacuum?
Okay, this guy? Well,
yeah, I would say, would you distinguish saying that this is a 0 as a state, or
yeah,
is taking you to a
just 0
superselection sector?
It's 0 as a state. This argument holds in QFT and CFT. It's just yeah, it shows that this thing is always 0. Okay. Other questions? Yes.
So the light transform argument is valid regardless of whatever dimension and spin it has, right? Like it was completely general.
Yes.
Okay, so I assume that it's probably not an invertible transform also. Otherwise,
oh, that's an excellent question. That's right. So the light transform is not invertible in general. It is quasi-invertible. It is sort of invertible on operators with unphysical complex dimensions and spins. So there is a Lorentzian version of these principal series representations. So earlier I talked about Euclidean principal series representations. There are also Lorentzian principal series representations. And when acting on those things, the light transform isn't quite invertible, but its square has a very nice expression. And I can tell you about that offline. But yeah, that's a fantastic observation. In order for the light transform to make sense, you need this condition. And this condition is not invariant under swapping delta with 1 minus j and j with 1 minus delta. And so you can't do it again. Other questions? Okay, so we get this, and then there's another term just by symmetry where 1 and 2 are swapped. Okay, and so now we have everything that we need to know to attack the inversion formula. So we've gotten a little bit more experience with Lorentzian representation theory and Lorentzian correlators, and all the facts that we need are on the board or in previous lectures, okay? So Okay, so now I'm going to try to answer this question of what on earth these analytically continued operators are. And all these subtleties about when continuous spin operators make sense, what kind of analytic structure their three-point functions have, will be crucially important in finding the right object to analytically continue. So let me remind you of something from the first couple lectures. So we talked about these partial waves, and the nice thing about partial waves was that they encode all of the information of the OPE of a pair of operators into one object. So we defined a partial wave as an integral over 2 points of a correlator and we only cared about 2 of the points transforming like primaries. The rest can be whatever you want. And let's say this is some physical correlator, so it's evaluated in the vacuum state omega. And we integrate this thing against a conformally invariant 3-point structure. And I'm going to use index-free notation now, so we have a z instead of having a bunch of indices. Okay, so this is a partial wave, and the amazing and beautiful thing about partial waves is that their residues compute particular operators in the OPE. So this, for any operator O star, is just a residue at delta equals delta star of some factors, some gamma function factors, times the partial wave. So this is a very good starting point to try to analytically continue the CFT spectrum in spin. We have a thing that contains the whole spectrum, so we should just try to analytically continue it in spin. But there's a problem. If we try to do this, does anyone see the problem? So as a hint, it has to do with the analysis that we did of CFT 3-point functions earlier. Yes?
Wouldn't the correlator on the left-hand side just vanish in the residue for non-integer spin?
Okay, good. So what I mean here, yeah. So let me be more careful about all of this notation. But yeah, roughly speaking, yes. So when I write the correlator without any particular ordering chosen, I mean a time-ordered correlator. And so you're basically on the right track. Does anyone want to take another stab? Okay, well, so I'll just say it. So the problem is that we did all of this in Euclidean signature, and let's think about this formula in Euclidean signature. So the key thing was to integrate against a 3-point function. And Euclidean 3-point functions with continuous spin operators don't make sense. They're not single valued. Okay, so that was something that we mentioned. And if you like, you can take this formula and you can Wick rotate it to Lorentzian signature. And that just turns all the Euclidean correlators into time-ordered correlators, Lorentzian time-ordered correlators. But then you have the same problem over again. It's just the same problem manifesting itself, which is that time-ordered correlators of continuous spin operators also don't make sense. Okay, so this thing cannot be analytically continued in J. Okay, so we need to do something to it to create something that can be analytically continued in J. And maybe you can guess what it is. What we should do is Wick rotate to Lorentzian signature and then take the light transform of the partial wave. So if that's not totally obvious why that's helpful, let me just write it down, and then hopefully you'll see. So we're going to take the light transform of P of delta J. And so what is this? This is something like an integral over Minkowski space of this correlation function it's a time-ordered correlator, but then the light transform is just going to hit this guy, right? The light transform is an integral transform acting on x and z. Those don't appear anywhere else in the formula, so it just hits this thing, and we're left with the exercise that we just did. How do you take the light transform of a time-ordered three-point function? So we did that exercise, and unfortunately you can't see the answer, but we got two terms. We got a theta function times the light transform of a Whiteman function. And the theta function had to do with when the light transform kills the time-ordered correlator and when it doesn't. So, so when we do this, we get the light transform of a Whiteman structure. And we get some restriction on x1 and x2 that had to do with this theta function that we got. So we integrate this thing and we get a theta function that relates x1 and x2 and x. We have some causal relationship between them. And so now I'm just going to write that causal relationship right here under the integral. So we get a term like this, and then there's a second term where 1 and 2 are swapped. Okay, so now here's the magical thing that happens. Now, everything can be analytically continued in J. So we talked about these types of Whiteman structures where the continuous spin operator is in the middle. These things were okay because the numerator in the three-point function could not wrap around 0. So it was completely single-valued in Lorentzian signature, and it makes perfect sense. So we can analytically continue in J because this is the only part of the formula that depends on J. And so this thing makes sense at continuous J, and so the whole thing makes sense at continuous J. And so it tells you that you should define an object so I'll call it funny O delta J plus or minus. It's defined as some factors out front that we won't care about times the integral of a product of operators. Basically what I'm going to do here is just strip off the rest of the things appearing in the correlation function and write an operator statement. And then there's another term where 1 goes to 2. And when you do this, so actually let me be slightly more explicit. So this thing depends on x and z. And so this thing will also depend on x and z. When you do this, you have to be a little careful. So you have to analytically continue differently from even and odd spin. And you can ask me about that later if you want. So we actually get two different expressions. One where you have a plus sign relating 1 and 2, and when you swap 1 and 2, and one with the minus sign. So we get two different types of objects here. And maybe if I have time later, you'll see why the difference between those two objects is important. But let me just let's just say what we've constructed here. We've constructed a thing such that when j is an integer, its residues are equal to light transforms of operators in the theory. So this is true when j is an integer, and minus 1 to the j is equal to this plus or minus sign by construction. Okay? It just came from harmonic analysis. We just used harmonic analysis to pick out O star, and then we light transformed both sides. That's all we did. But this thing makes sense for complex J. So the interpretation is that it gives an analytic continuation in spin of these things. Analytic continuation in J of these things. So you might remember a while ago I drew a plot of the spectrum of a CFT. And the funny claim from Karen Ho's formula was that there are curves, and the physical spectrum of the theory, the local operators, live as points on these curves. Well, not over here. This is the shadow region. Okay, so the physical spectrum lives here as points on the curves, and what we're finding is that that's not precisely true. That's a misleading statement. It's misleading because you cannot really analytically continue local operators, but you can analytically continue their light transforms. So the claim is that this Riemann surface is the spectrum of light ray operators in the theory, not the spectrum of local operators. And that these special points correspond to light transforms of primary operators. So for example, this point here is the light transform of the stress tensor, and this point here is the light transform of the next spin 2 operator in the theory. And this point here is the light transform of the lightest spin 4 operator in the theory. So these light transformed operators fit together into a more rigid structure than just the local operators. Questions?
So David, in the S-matrix theory, you can also do these things, and there is also this analyticity in spin.
Yeah.
But usually people talk about radio trajectories, which is sort of continuation through particles. And is there an analog of this light ray thing that will allow you to interpret the points on the particle physics radio trajectories?
Yeah, that's a good question. So I think it's closely related to the question of what these things look like in the bulk. So Sasha's question was, how do you make sense of continuous spin things on the Reggie trajectories for amplitudes? So I don't really know. In the bulk, it seems like these objects correspond to some kind of stringy shock. And maybe the clearest statement about that is, hopefully we'll talk about the light ray OPE if there's time. So you can take OPEs of shocks in the bulk, gravitational shocks or conventional shocks, just obtained by integrating local operators, and you can take an OPE where they become coincident. And when that happens, you get some kind of stringy shock. And that's in ADS, but I think the statement would be that in flat space, what you're doing is scattering stringy shocks of some kind. So somehow there's a generalization of the types of external states that we usually consider for scattering amplitudes to include continuous spin external particles. These are not the continuous spin particles that, so everyone who reads Weinberg, like, you know, there's a part where he says, oh, you know, by the way, you can have these continuous spin representations, but they don't make sense, and so we don't see them in nature, so we just ignore them. And then there was some recent work by people trying to make sense of these things. So those are completely different objects, so I want to make clear. I'm pretty sure that those are completely different. They transform in a different way under Lorentz transformations, although I'm not totally sure. But anyway, yeah, the claim is that there is indeed some kind of continuous spin deformation of the external states, at least in sufficiently nice theories. I would say like in string theory. Other questions? Yeah.
So if I understood correctly, the lines stop at j equals to 1?
Okay, great. Yeah, that's right. So we actually don't know what happens down here. So I would say that they probably don't stop. They probably keep going, but we don't know where they go. The inversion formula doesn't describe that region, so it's kind of hard to know. I guess the best statements we have are in n equals 4 superpositing Mills theory in the planar limit. Then there's a beautiful picture of this whole Riemann surface. And you can see what happens. And I actually don't know what happens to these higher trajectories. Maybe Amit can tell us. Do you know? Do you know what happens to these higher trajectories when they go down to this region? In general, no. Okay. So there's at least a very good understanding of this leading trajectory, and it basically if we add an extra direction, a complex direction, then this point here is a saddle point, and it goes down in this direction. And there's actually a second sheet that this thing. Well, there's a nice story there, and there are some plots you can look at if you want, made by. Well, I guess he's not in the room, but people who are around. So I can tell you what plots to look at. Other questions? Yes.
Okay, so you've been talking about this continuous spin, and I was wondering if this has to do anything with anyons in 2+1 dimensions.
Not as far as I know. Yes.
Just to clarify your previous comments, but this, when the spin is not integer, annihilates the vacuum. So when you say about that, when you think of it as a state, I get a bit confused. What is the state that you're talking about?
Yeah. It's not. It's not really a state. That's an important point. It doesn't create a state, and so in the context of amplitudes, it's not going to be an in state or an out state. It's more like when you have an amplitude where some particle is propagating through a background. It's like a background that transforms in a nice way. Yeah?
Do we know anything about the topology of the Riemann surface in general?
No. No. There are lots of mysteries about this thing. We need more examples. Okay, good. So you have to listen to me talk more at the end of the day. So the goal at the end of the day will be to use these things to prove the Lorentzian inversion formula, and then hopefully I'll have time to talk about the light ray OPE, which is a very natural place where these really funny continuous spin operators show up. Okay, thanks a lot.